Hey everyone, welcome back. In this video, we're going to talk about real-world operational amplifiers. I consider this lecture to be one of the more important ones inside of this course. If you're a university student or somebody that's read a lot of textbooks about electronics, you've probably encountered many different operational amplifier circuits like we saw in the previous section, but all of those questions most likely assumed an ideal operational amplifier. So in this section, we're going to change that. We're going to challenge you to get much more practical with real-world op-amps and show that you can tackle the most complicated interview questions so you can prove to the interviewers that you actually have worked on these operational amplifiers before. Real-world op-amps obviously have a lot of non-idealities, more than I can even list, and we're going to get into the vast majority of the important ones here today. Be sure before we get into it that you look at all the resources and questions and answers that I've attached as resources to this lesson, as we will not be going through every single one of those questions and everything that I've linked. Now, from the last session, we know what ideal op-amps look like, but what is a real-world op-amp? So of course, a real-world op-amp still is an amplifier. Its purpose is to become as close to an ideal operational amplifier as possible. However, it has many non-idealities. So before we dive into questions, let's take a look at some of those non-idealities. The first of which is that an op-amp typically has finite open-loop gain. What this means is that an ideal op-amp has infinite gain, as we talked about, but a normal op-amp has a finite gain. It's a number less than infinity. Typically, for most op-amps, it is somewhere north of 100,000 volts over volts. So if you have a 1 millivolt input, let's say, in between the non-inverting input and the inverting input, then it will multiply that by 100,000 times at the output, which almost always will saturate it to VDD or VSS. Next, an op-amp has a finite input resistance, so it is not infinite. What that means is that looking into each one of the inputs, both the non-inverting and the inverting, you will see that there is some sort of finite input resistance. So what that means is that there is going to be a resistance looking into the non-inverting input to ground, and there also will be the same at the inverting input. However, we should also remember that there will be some sort of resistance in between the two inputs as well if we probe across them. So there's actually three types of input resistances here. More than just input resistance, there's also input impedance. There's going to be some amount of parasitic capacitance in parallel with these resistors, both in between the inputs and ground, as well as in between the inputs together. This can have effects at high frequencies. The next thing, as a result of having a finite input impedance, there is going to be some amount of current that flows into the inputs, and this is known as the input bias current. Each one of the inputs, both the non-inverting and the inverting input, is going to have some amount of current that flows through it. We'll call it I1 and I2. These are called the input bias currents. Without these currents flowing into the inputs, the op-amp will not work properly. But the majority of cases, these two currents are different than one another. The difference, I1 minus I2, is known as the input offset current. It's the difference in between the two. And this can have really interesting symptoms in negative feedback circuits. The problem with having a high input bias current is that it can cause a voltage drop across external resistive components, causing your circuit to behave weirdly because V equals IR. If you have I, then you're going to have a voltage drop. Next is an incredibly interesting fact. Due to the inherent nature of operational amplifiers, there is going to be some offset voltage known as the input offset voltage, VIO, that will cause the output to be at 0 volts. Now you might think, well, in an ideal op amp, this is just 0, right? If the difference between the two is 0, then the output is going to be 0. But in a real world op amp, you actually have to bias this op amp to a certain voltage in order to get the output at 0. It's not going to be perfect. For some op amps, this can be very, very close to 0, but for a typical general purpose op amp, this is going to be on the order of 1 millivolt. So you have to apply a 1 millivolt differential across the non-inverting input and the inverting input in order to actually get 0 volts at the output. We'll take a look at what happens if you apply 0 volt differential at the input as an interview question. Let's take a look at the next one. An ideal op amp has 0 output resistance, but a real-world op amp has a finite output resistance. And what this means is that it doesn't have the ability to source as much current as you want. And if your load resistance is somewhere on the same order of magnitude as your output resistance, then you could have a serious voltage drop across it and cause serious issues to your negative feedback circuit. An op amp also has a finite slew rate. That means if the op amp output is switching from high to low very quickly, or it's moving, it's going to have a maximum slope. Slew rate is really just another fancy term for the word slope, where slope is defined as the delta V over delta T. Basically, how fast can the output voltage swing as a function of time? Next, an op amp typically has a finite bandwidth. That means at high frequencies, it's not going to be able to perform and have the same gain as it did at low frequencies. And typically, this is also a function of gain. So many op amp datasheets will actually give you what is known as the gain bandwidth product, expressed as dB multiplied by hertz, where you have a choice of trading off either the gain of the op amp for its bandwidth or its bandwidth for its gain. So if you have a 1 dB per megahertz gain bandwidth product, that means if you operate the op amp at 1 megahertz, you can only have 1 dB of gain. But if you operate the op amp at 1 kilohertz, then you could have 1,000 dB of gain. Next, an op amp has finite common mode rejection. So typically, an op amp is only supposed to amplify the difference between the non-inverting input and the inverting input. But let's say you had a sine wave at the non-inverting input and the exact same sine wave at the inverting input. An ideal op amp would just subtract these two and give you 0 volts at the output. However, a real-world op amp will not do that. It will have some finite common mode rejection, and typically this is going to be extremely high on the order of 80 to 100 dB, but you're still going to get a very small signal at the output that kind of looks similar to the common mode input. Another similar rejection ratio is known as the power supply rejection ratio. If there is some amount of noise at the input terminals of the op amp power supplies, that could couple and go into the output. And the power supply rejection is a measure of an op amp's ability to filter out this noise in the power supply from its output. This is also typically on the order of 80 dB to 100 dB at DC. However, both of these ratios, both the finite common mode rejection and the power supply rejection, are functions of frequency, meaning that at higher frequencies they get worse. An op amp, because of all of these things, especially the finite bandwidth and the fact that it can have inputs that receive bad feedback from the outputs because of bad common mode rejection or bad power supply rejection, can get into a condition where the op amp can oscillate. So as an example, if you have some sort of signal or noise on the power supply, and it gets coupled into the output, even if it's really small, and the output is connected back into the inverting input through a resistor, for example, because it's in the negative feedback configuration, you're still going to have some amount of noisy signal here. And then that is going to be amplified. And again, the output will become larger and it will go back and create this positive feedback loop, which eventually might cause the op amp to oscillate, which is undesirable behavior in most circumstances. It might make it unstable. That's just one example. An op amp internally also has some amount of noise. This could be thermal noise or other types of noise, where it itself will add some amount of noise factor to your signal. Even if you give it perfectly clean signals, both for power and input, the op amp itself might add some noise to the output. The op amp is also extremely sensitive to temperature effects, just like a normal transistor is. When the temperature goes up and down, this can have very interesting effects on the input bias currents, on the offset voltages, on the common mode rejection capabilities, the power supply rejection capabilities, and specifically the noise. Typically, the higher the temperature, the more noise we get. So these are some of the differences between ideal operational amplifiers and real-world op amps. Typically, the one that we are most concerned about is the input bias current. This is generally the most important thing about these op amps because they have the ability to truly affect a huge voltage gain on large resistors if large resistors are used in negative feedback configurations. The second most important, well, it's kind of hard to actually say what is most important, but the things I have come across as most important are the finite gain bandwidth product as well as the input offset voltage. We're going to get into questions regarding all three of these topics, but before we move on to interview questions, I want you guys to try an assignment. Open up the next lesson. It's going to be an assignment, and I want you to go inside of the LM741, which is a very general purpose operational amplifier. This is what it looks like. And I want you to go into that data sheet and find the 10 non-idealities that we discussed in the last slide inside that data sheet and document it. See if you can find it, and then we're going to go over it together. I'll see you in the next lecture.